Hey everyone, you might remember my last video. Don't worry, if you don't, here's a brief recap.
In that project, I and my team developed an autonomous reconnaissance ground robot using Turtlebot 3. The robot was able to carry out SLAM and frontier exploration in an unknown environment. It also detected April tags, which represented victims in a disaster situation. Yes, it was not perfect, with a lot of room for improvement. However, it was a successful implementation of the concepts we learned in the classroom onto real hardware. And it was fun.
In this video, I'd like to share a small extension for this project that stems from a component of my master's project. My master's project involved a planning problem for energy aware frontier exploration with a UAV. Okay, what does that mean? Robots have limited energy. If a robot is exploring in an unknown environment, which is hazardous for humans, you do not want your robot to get stranded because of a lack of energy. So I want my robot to carry out frontier exploration while considering energy limitations. One solution is to return to the base station for recharging and then head back for exploration and keep doing this until you're done exploring. How can we achieve this using a turtlebot? The answer to this question comes from my project's planning part. Almost everything is the same from before, with one exception. I am modifying the original explore-lite ROS package to prioritize my frontiers. The strategy for prioritizing is adopted from this paper. The first step is to find those frontiers, and that is unchanged from the original package. Next is I filter those available frontiers using a safety constraint. This safety constraint gives a theoretical guarantee that the robot will always return to the base station without losing energy, or in other words, it will never get stranded. After filtering the frontiers, I sort those frontiers with the cost function. Based on this cost function, the robot will move towards the frontier having the lowest cost. And the robot will continue exploring like this until no possible frontiers are left. No possible frontiers. I say that because there might be some frontiers left to be explored, but they cannot satisfy the safety constraint. So it is not possible for the robot to explore some frontiers and also come back without getting stranded. Any limited energy robot can only go so far and also come back with a certain amount of energy.
I could not walk on the robot this time, but here is a gazebo simulation to show the implementation. The robot's starting position is considered as the base station, marked by the green marker. The robot starts exploring, and here it decides to return to base station for recharging. Charging in this case is considered instantaneous, after which the robot heads back for further exploration. The robot ends the exploration here, but we can see some unexplored area the robot did not go for. This is because those frontiers are either smaller than the minimum frontier size or are not safe to go to. Let's see how this compares to explore-lite's greedy strategy. This plot shows the comparison between the two in this specific environment. The orange line is explore-lite, while the blue line represents a proposed energy-aware strategy. There are three key takeaways. The greedy strategy explores a bit faster than the energy-aware strategy. However, the energy-aware strategy explores 98% of the total area, significantly faster than the greedy strategy. Lastly, the greedy strategy is able to achieve almost complete exploration, but this is not true for energy-aware strategy. And it is okay, because the greedy strategy assumes infinite energy. The proposed method achieves safe exploration with limited energy and is faster until the 98% mark. I want to talk about some of the drawbacks of the proposed strategy. First is hyperparameters. The performance varies with multiple factors, including 4 weights that I have used for the cost function. Second is the environment. The performance also depends on the environment that the robot explores in. And third, which is the most important, I think, is the area size limit. Since the robot has to come back to the base station for recharging, satisfactory exploration cannot be achieved in larger environments. The last two drawbacks can be addressed using a team of a UAV and a ground robot working together, where the UAV does exploration while the ground robot serves as the moving charging station. I might work on that in the future, but bye for now.